I'm going to look at two function transformations today, shifting and stretching. To start with, I'm going to use a simple function, just a simple straight line, the line y equals x. If I want to move this function up or down the axes, I'm going to have to add a parameter or subtract a parameter. I'm going to choose to add 2. That's the standard straight line graph, and I've moved it up from the origin by 2 points. To look at this in function notation, f of x, which was the original x, has been transformed by adding the 2 into a new function, and the new function is the f of x plus the additional parameter, which I'm going to call v, the general vertical shift parameter. Let's look at this on the graph. Here we have a graph showing, in fact, two straight lines, one on top of the other one. The first one is f, our original line, you can see that highlighted, and the next one is g in red, the shifted function, where I've added the vertical shift parameter. When I change that parameter away from 0 and I move it to the value of 2, you'll see that my red line moves up the axis by 2 units. The new equation of that line is shown in red. It's x plus 2 as we originally intended. If I want to look at a negative shift, I move the vertical shift parameter to a negative value. The line moves down the y-axis, and the new equation is x minus 1.
Let's look at what we would do to get a horizontal shift this time. For the vertical shift, we took our function and we added and subtracted a constant. To shift along the horizontal line, you add and subtract a constant as well, only you do it to the independent variable. Now that looks a little bit confusing if you're not familiar with function notation, so let's look at it with the y. If I had y equals x, that was my f of x. I want to look at it when I change it to x minus h. Everything that was an x changes to an x minus h. So we can rub out the x and write x minus h, which looks exactly the same as what we wrote before, but the sign is different. Let's look at it on GeoGebra.
Again, I have the straight line on the graph. This time the straight lines are 3 on top of each other, the original function in green with the horizontal shift applied to the x, and the function in red with the vertical shift. Originally I start with no shift at all. When I move my horizontal shift positively, you can see that the green line moves in a positive direction along the x-axis. This positive direction causes the y-intercept to drop. So a positive vertical horizontal shift is a negative vertical shift. When I move my vertical indicator, you can see that the red line moves up the y-axis. And again, a positive vertical shift has the same effect as a negative horizontal shift. You look at the equations of the lines that have been generated, you can see that the vertically shifted line has a positive 1, and the horizontally shifted line has a negative 1 added, which is the y-intercept. So again, a vertical shift and a horizontal shift have the same effect on the line, but in opposite directions. One is positive when the other is negative.
The next kind of transformation I want to look at is a stretch or a shrink, and we'll just look at both directions at once. So imagine if you had a box and you wanted a box that was 3 times taller, well, you would need to change, okay, I'm not great at drawing, you would change the height into 3 times that height. So your transformations become multiplied. Again, if I wanted to take that original box and draw something that was twice as wide, I would have to multiply the width by 2. So here you're going to see I'm going to do the same thing with my function. If if I'm doing a vertical stretch, let me move that down so you can see. If I'm doing a vertical stretch, then I multiply the entire function by the value of the stretch. If I'm doing a horizontal stretch, then I multiply the x by the horizontal stretch. With a straight line, if I multiply the whole function by 2, 2 times y is x is y is 2x. And if I multiply the x by 2, I also get y is 2x. So regardless of what stretch you do, when you're looking at a straight line, you get the same effect.
To show you the effect of that on the graph, I've got 3 functions here. There you can see the definitions of them. The green function has the horizontal stretch applied to it, and the orange function has the vertical stretch. Let me just show you those again. You can see the definitions. Right, so to start with, I'm going to increase the vertical stretch. This is the parameter that I've applied. And as I increase that stretch, you'll see that orange line start to shift away from the others. And there it goes, and it's becoming steeper. This is what you would normally expect. You can see the vertical shift. The equation is y equals 2x, because I've applied that stretch to the entire function, as you can see in the definition. Let's see what happens when I apply the horizontal stretch and shrink parameter. As you can see, it has exactly the same effect as the vertical parameter. But when you look at the definition, you can see that it's actually been applied inside the brackets to the x. Now in a straight line, that doesn't make any difference. We don't need the horizontal anymore, so I'll just put that back to 1, get rid of the effect of that, and have a look at what happens when I adjust the vertical parameter again to something less than 1. As you can see, that squashes it vertically and flattens out the line.
So to sum up the transformations that we made to our original function, we shifted it vertically by adding, subtracting a vertical shift parameter. We shifted it horizontally by adding or subtracting a horizontal shift parameter to the x, which made no difference in the case of a straight line. We stretched it vertically by multiplying the whole function by a vertical parameter, and we stretched horizontally by multiplying the whole function by a horizontal stretch parameter. Now if we put all of those together
on the graph, you'll see that we can have a number of effects. There was the vertical shift, there goes the function heading up 1 unit. Now I apply a positive horizontal shift, and as you can see, it completely counteracts the effect of the vertical shift. So let's take that one away. Here is my vertical stretch. As I shift that upwards, I get a positive slope to the graph. I can bring that down and all the way around, in effect flipping the graph over and giving it a negative slope. So this doesn't really fit the sort of stretch idea, because as soon as you've got negative, you've actually changed the shape quite substantially. Have a look at the horizontal stretch parameter. You'll see that it has a similar effect to the vertical parameter. Now if you're looking at all of this and thinking, well, what's the point? It's a straight line. You'd be right. When you really start to see the benefit of thinking about it in terms of transformations is when you make the function a little bit more complex. So let's look at a parabola. Change my original function into an x squared and apply the same transformation. There's my vertical transformation, and you can see the parabola moving nicely up and down the y-axis. There's the equation with the vertical shift applied. Purple equation has got all the shifts combined. Now I move my horizontal shift. Unlike a straight line, the horizontal shift has a distinctly different effect when you look at the parabola, and in fact it moves the parabola along, which is different. When you look at the equation of the parabola in the purple, you can see what that's done. I'm going to look at what that's done to the turning point, and I use this extremum function that shows me the point A, the turning point. You can see the turning point is at 1 minus 2. Now 1 minus 2 in that purple equation are the vertical shifts. Here I'm doing a horizontal stretch, and that makes the graph tighter or wider. It changes the shape. Now again, you're thinking, well, that was great, but I knew how to do the parameters in the first place. But where this really comes into its own is when you look at more complicated functions like the trig functions. And for a trig function, every single one of these transformations has a different effect. There's the original function, it's just my sine of x, and there's my transformed function holding the values that I put in for the parameter. There's my vertical shift. As you can see, that shifts the line about which the function oscillates. Horizontal shift, as you would expect, shifts it up and down the axis, and looks like you can see the wave traveling up and down. It's a phase shift, if you think about it in trigonometric terms. Your vertical shift changes the amplitude of the function. In other words, the highest and lowest values that that function can achieve. And your horizontal shift changes the period of a trigonometric function. So instead of trying to remember what each parameter does in your trig equation when you're sketching your trig function, you can think of what kind of transformation it's done to the original.